All right, let's get started. So you might remember that we drew this conclusion where, in terms of the sizes and storage capabilities of storage devices, looking at just one company, Intel. We all know Intel, right? Back in 1971, they had a memory chip with unreasonably low storage capability in today's standard, 1 kilobit to be exact, because lowercase, as you see. But the same company had 32 gigabytes of storage capability in 2021. So which is basically 32 million times increase in storage capability within 50 years. Just to show you how crazy advancement we have had over a period of few decades. We also talked about how the storage requirement is increasing. The amount of data that we're creating is exponentially increasing over the years. And also the revenue, basically the money that the companies can make by selling storage systems, is increasing as well, which is a great sign for anyone who is interested in memory or learning about memory or working on memory. We also looked at some market insights about DRAM manufacturers, specifically why DRAM. You might remember that I showed you a pie chart where DRAM and flash memories basically took up more than 90% of the market share, right? The others were like a meager amount. So we do care about what happens to DRAM and flash memories. And I pointed out some key players, some of which you probably heard about. Some of these were like brand new names for you. Regardless, there are many stakeholders in the game, but most importantly for US market, Micron is the biggest player. So I want you to know that. Intel is also involved to some extent, but not for every memory. Intel is not really that big in DRAM. I mean, they don't have any footprint in DRAM at all. They work on flash memory, but recently, not too long ago, they kind of almost sold their memory business to SK Hynix, a South Korean company. Okay, and basically that's why you don't see Intel, doing that much moving forward for non-volatile storage specifically. All right, then I think this is the slide where we stopped in the last class. Right? We started looking at it. This is an interesting statistics. It shows enterprise spending on cloud and data centers from 2009 to 2021. And again, you see another almost exponential trend. So spending in cloud storage and data centers is increasing. Why? People are observing a trend where we no longer want to just keep buying memory cards or SSDs and keep our data to ourselves, because that's too risky. What if you lose the storage device? What if basically it crashes, right? So you want to make sure that you store it with someone like Microsoft, Google, Amazon, like some sort of established entity that could assure you that your data will be safe. But how can they do that? I mean, basically, if you buy a storage device, why can't you assure that this data will be safe? Because you have less redundancy. But the other players like data centers, they have more redundancy. They store your data in multiple places. So there will be backups of backups of backups, right? So that means whatever amount of data that these data centers are storing, you have many times more that data, being stored somewhere in some form. So you have to keep that in mind. But also, just take a look at what happened from 2009 to 2021. Notice one color is getting more dominant, right? Notice that? That's cloud infrastructure. So basically we are moving towards cloud more so than what we used to do in the past. Why am I telling you all this, right? This is a very quick overview. I'm not trying to teach you marketing or like business oriented stuff in any way. But if you're not aware of where things are headed, it's very difficult for you to pick and choose the technology, right? So cloud storage requires a very different kind of infrastructure versus like a flash drive. Say if you're trying to just carry it around, you have a different set of requirements like area efficiency, weight, energy efficiency as well. If the moment you plug in the flash drive to your laptop, it starts taking too much power and it drains the battery. Will you use it that often? Probably not. I don't know if you have tried that, but if you plug in an SSD on your laptop for a long period, maybe you're running a video editing, some sort of video editing on an SSD, you'll see your battery will drain faster than usual. The reason is that thing needs to be powered up. So for those kind of storage devices, your priorities will be energy efficiency, maybe speed to some degree, but not to that degree. But for cloud storage, you're not basically carrying it around anywhere. It's stable, stuck in a room. So it could be larger. You don't care about area efficiency to that degree. You may not care that much about energy efficiency because you can power it up with, a dedicated power supply, for example. Unlike laptops or other portable devices where you have to charge it over and over again. So that's why shifting to cloud storage opens up possibilities that was otherwise impossible. And I can give you one name that we will discuss here in this lecture. Not in this course. That is cryogenic memories. How many of you have heard about the term cryogenic memory? Maybe, yeah, some of you. That's great. So you cannot even imagine having cryogenic memory in a daily commodity. Like you cannot just carry it around anywhere. But when you are moving to data centers and cloud type storage, you can definitely think about those kind of stuff. So we have a dedicated lecture on cryogenic memory. Here is why. We need to discuss that seriously. If I were giving up this lecture in 2014, there wouldn't be a lecture on cryogenic memory. Okay. All right. Anyways, moving to the next one. Wanted to also show you the trend in general. Number of data centers in the world in 2021. I only have data up to 2021, but you can easily imagine the data moving forward. US is leading the world in terms of data centers. In fact, I just heard from a colleague, I cannot independently verify that US has stopped giving out new licenses to data centers because they're struggling to find ways to power up these data centers. It takes so much power to run these data centers, by the way, right? It's taking away power from households, for example, or other sources. And there are many other countries who have data centers, but in general, the number of data centers is increasing, right? You might be, why data centers? Because we are generating a lot of data. You might be wondering from which source? Who is the culprit here? Well, there you go. That's your answer. From all possible sources that you could possibly imagine. And surprisingly, banking almost tops the list, right? All the transaction that you're doing, all this, money that you're putting from here to there, all these shares that you're buying, all this cryptocurrency that you're, dealing with, they create humongous amount of information and they need to be saved. Maybe you don't care about, the coffee that you bought 10 years ago with your credit card, but they still have to keep track of that. And maybe you go back one day and just decide to check out that, random charge that was in your credit card. Who would have known, right? But they have to give you that option. They have to keep record of all of these transactions. And this is just a simple example. Just imagine, consider that as one transaction and multiply with trillions and trillions. Then you get the idea how much data they have to preserve and continue to preserve. And also, I'm not even mentioning cryptocurrency and other things. These are more complex to explain. More importantly, automotive sectors, well, how many of you use Google Maps? Almost all of us use Google Maps. It's almost given that, oh, Google has everything. But Google has all this information stored somewhere, and they're continuously updating it. So that takes a lot of data. I'm not going to go through the entire laundry list, but you get an idea as to who could be potential users of these data centers. Now, with that, this is probably the most critical challenge in our time that deals with data and energy, okay? That is AI and other, not just AI, but other high-performance computing systems, including supercomputers around the world, they take up humongous amount of energy. You cannot even imagine how much. Just Google it. I think I did mention that in the last class, that already ChatGPT and other large language models take more energy than some countries take in a year. So this is a statistic that is being thrown out every once in a while in discussions. So these numbers are crazy, and they're increasing exponentially. Notice this is the total global energy demand across everything that you can possibly think of. This green one is specifically for data center. And notice data center energy demand is increasing rapidly, right? So, there was a time in 2010, it was kind of negligible if you compare it with today's standard. So how can we keep powering up these data centers? And they're only going to keep increasing, as you have seen in the other trend. We are generating data exponentially. And whatever we are generating, they're here to stay. So we will continue needing more and more data centers and storage systems. What do you think data centers have inside them? memory devices in general, right? Essentially. So depending on what kind of memories they can store the data in, they may have more expense or less expense. So they do care about innovations in storage capability. Okay. Some other crazy statistics, I'm not going to go through all of them. Please take a look at it if you're interested. I just want to show you the power of large numbers. Okay. 50 billion smart and connected devices already by 2024. 50 billion. Just imagine that, right? Anything that if you multiply something with billion, that will look bigger. So if you generate 1 byte, easily it's 50 billion bytes all of a sudden. And you are not generating 1 byte, trust me. A single selfie will be easily infused even 10 megabytes, depending on which cell phone you have. And 7 megabytes of new data per second per human being is being generated. Let me take a step back and ask you one more thing. How many memory devices do you need to store 1 bit of data? 1. So if you're generating 7 megabytes of new data per second per human being, you need that many memory devices to be created in the world per second for per human being. This is unbelievable. Like, you see why we should care about this type of stuff now? Okay, anyways, I'm not going to go through all of them. These are crazy statistics. Okay, wanted to show you the evolution of digital storage devices. And I think I showed you a history, like with some images in the last class, but I want to make it focused now. This is mainstream. For the longest time, like more than 40 years, even more than that, people relied on 2 to 3 types of memories: SRAM, DRAM, and flash. 3, that's all. Flash is like more relatively new version of memory. So SRAMs and DRAMs have been there for forever. Okay, and notice they're just simple circuits that uses transistors. These are all transistors. So you make a circuit out of transistors, and you power the circuit up, and that circuit holds some information. That also means you have to keep them powered up all the time. There is no way you remove power and the circuit still remembers what it was storing. That's the biggest problem with this type of memories. We never cared that much in the past because we didn't have to deal with that much data. But now that you have humongous amount of data, you need humongous amount of these circuits and devices. That means you need extremely unreasonable amount of power to continue storing anything in them, right? Okay, so that's why we have started looking beyond. By the way, we will go over the details of SRAM and DRAM. So I'm just skimming through it. Okay, flash memory is another very important memory that we will also discuss in great detail in this course. But emerging memory, we may not have the same amount of detail for emerging memory in this course, but we will have decent amount of detail specifically about the first one, MRAM. Did I tell you that anything that has 2 physically stable states could theoretically be used as a memory? I gave you examples of DNA, magnets, spintronic devices, right? Ferroelectrics. You see the realization of that vision here. PCM is the phase change memory that I talked about, that transfers itself from amorphous to crystalline and back. And depending on whether it's amorphous or crystalline, you could represent 1 or 0. Ferroelectric memory, where is that? Yeah, this is the one. The name doesn't do justice. It's like a short form. This stands for non-volatile ferroelectric field effect transistor, like a mouthful. But we will have a separate lecture on them. Don't worry. We'll get there. So we basically use ferroelectrics to store information. Here we use a material that could be amorphous or crystalline to store information. Here, this is an oxide RAM. This is fun actually to talk about. Notice these bubbles, these are oxygen vacancy, basically. Just treat them like oxygen for a second, like bubbles. If the bubbles create a bridge between these 2 electrodes, you have low resistance. If you break the bridge somehow, you have high resistance. So depending on whether you have a bridge or not, you could represent 1 or 0. So that's an oxide RAM. Another physical mechanism to store information. Okay, conducting bridge RAM looks very similar to oxide RAM, but instead of oxygen, they have a different metallic atom. It's okay. We'll get there later on. My point is, all of these devices are capable of storing 1 bit of information, and they're much smaller than SRAM. Notice, this is just 1 transistor. It doesn't look like it because it's a 3D structure, but instead of having 6 transistors, You have just one transistor here, being able to store one bit of information. So typically, these emerging memories are smaller. So this is a general trend. We're trying to make them smaller because we need to have more of them to store more information. We'll go over almost all of this that you see here in this course, and possibly more. All right, yes. Yes, thank you. Thank you for pointing out. Yes, I didn't, want to go over this now, but we have a separate lecture on ReRAM. We'll go over all of them, basically, that you see here, and possibly more. Like in the cryogenic lecture, we'll talk about even superconducting memory, and just what are the odds, right? Anyways, so just wanted to sneak in one simple slide about computing, because that's related to memory. And we are getting to the slide where computing and memory will come together and see the dynamics of them. Evaluation of computing power. We started with 4004 microprocessor, which was the very first processor in the world. And gradually we diverged towards more advanced processor, right? What's common in all of them is that the transistors are there. We keep using transistors, and transistors help us process information. What we did over the years was we made the transistors smaller. And by doing so, we managed to put in more of them in the same area. Similar to what memories do, you need one memory device to store one bit of information. Similarly, you need at least one transistor to handle one bit of information, to process. Actually, in reality, you need more than one transistor to handle. But at the very least, you need one transistor at least to handle one bit of information. When I say handle, it's like processing one bit of information, not storing. Okay. So the more transistors you have, more data that you can process. Okay. So imagine 10 years ago, the cell phone cameras were not as advanced as they are now, right? Maybe we have, 1 megapixel, say. Now we have, 50 megapixel cameras. So 1 megapixel. So it took less transistors to process that single image that you took. Now you have more advanced camera, so it takes more transistors to process that information. But you don't spend more time to do that. How is that possible? Because you have more transistors packed inside your processor, being able to handle all of those information in one shot. Okay, all right. So keeping that in mind, yes. Sure, of course. That's a great question. So apparently, this basically relates to how fast your transistors can switch from on to off. Okay, so for example, if it is a gigahertz, it represents 1 nanosecond switching time, basically. So it takes 1 nanosecond for the transistors to go from on to off, or vice versa. Obviously, there are some other factors, but it's a rough estimate. Okay, like 1 gigahertz will not always transfer to 1 nanosecond, but you get the point, like close to that. So basically, your transistors are not just getting smaller, which obviously I wanted to make it easy to explain. They're also becoming faster because of other reasons. We are making the channel length smaller. We are using advanced materials with higher mobility so that they become faster in general. By doing so, we are enhancing their speed. Okay, so it's not just we just have more transistors, we also have better transistors. That's the other thing that I kind of skipped. Okay, so look at the memory, by the way. We'll get back to this type of comparison more often in this course. Every time we finish a lecture, we'll go back to a chart and compare that against the other things that we covered in the past lectures, okay? And see what are the pros and cons. Will it win over all the other candidates, or will it lose, right? Every time we finish one specific topic about memory device, we'll go back and explore that. But just wanted to familiarize you with this type of a notation. This is known as a spider diagram in memory research. The outer end, depending on how many parameters you have, it could be octagon or more, doesn't matter. That represents the dream combination, the dream memory device that you're trying to create. Meaning it has to be highest speed possible. Scalability means how small can you make them? The smaller, the better. Okay. Energy efficient, of course. Who wouldn't like that, right? On-off ratio. Why do you care about on-off ratio? If a switch gives you only a meager difference between two states, it will be extremely challenging for you to sense that information. And there could be misreading, as you can imagine, like cat to bat, right? But if you have a higher separation between 1 and 0, meaning higher on-off ratio, that's better. So you care about on-off ratio. Many other things, of course. But I'm not going to go through each and every one of them. Every line that you see inside, they represent a different technology. We haven't discussed any of them, so I'm not going to try now. We will get back to it after maybe towards the end of the course. Point is, it could be ferroelectric, it could be resistive RAM, it could be MOT memory, it could be molecular memory, doesn't matter. None of them are ideal. Like none of them could approach the most ideal kind situation as of yet. And notice all of these are emerging memories. So that's why that's a good and bad news. Bad news for industry that they don't have a solution yet. Good news for everybody else, like including researchers and students like you, because there are opportunities and it's an open playing ground. If people figure out a way to solve all of them, sure, yeah, there is nothing else for you to do, at least for the next 10 years, until they run into the next problem. Okay, so now that they're exploring actively for possible solutions that could achieve a dream combination, there is a lot for us to explore. Okay, I want to also quickly familiarize you with some metrics that we will care about throughout the lecture, throughout the course, that are specifically related to memories. So what are the performance metrics? In short, it could be scalability, how small can you make them? Speed, obviously, who doesn't care about speed? Power, everybody cares about low power, of course. And also reliability and variability. And I'm going to go a little bit deeper into this to explain what they mean. And when we go through lectures, we'll address each and every one of them for every specific technology. Let's start with the end first, reliability and variability. Retention. What does retention mean? For a memory, retention means how long can the memory hold on to the data and could still allow us to reliably read the data, okay? For SRAM, static random access memory, the one that I showed you, which is mainstream, how long do you think the retention time is? Can anybody guess? You are right and wrong. Here is why. And thank you. I mean, I really appreciate you guys answering questions, okay? Please try to do that. Thank you so much. You are right in a way that as long as you keep the power on, it will hold the data forever, right? It has infinite retention, essentially. But the moment you turn off the power, it's gone. It's in that sense, there is also zero retention. So it's a very tricky memory. Nobody wants to use them anymore for large scale storage. You know why? Because if there is billion SRAM that you need to power all billion of them, which is a nightmare, essentially. So trust me, no data center uses SRAM to store information. That's the reason, simple reason, okay? So think about ferroelectrics, okay? A ferroelectric memory, depending on which ferroelectric material you're using, could hold on to the data even after you remove the power, by the way. I'm taking some random number. I will give you the real numbers later on, okay? Maybe for a few seconds. What does that mean? That means every few seconds, we'll have to power it on and reprogram to make sure it doesn't lose the data. DRAM, dynamic random access memory, is kind of in between SRAM and others because they don't instantaneously lose the stored data because there is a capacitor. Capacitors don't just give up charge like this, right? There is a time that they need to discharge gradually. And you'll be surprised to know the time is in microseconds. Okay, it's like less than blink of an eye, obviously, many times less than blink of an eye. So you have to keep refreshing DRAM. That's the bigger challenge. It's better than SRAM, but in terms of energy efficiency, but not as good, obviously. Microsecond is nothing. On the other hand, there are memories like phase change memory, for example, who in theory could hold on to the data for years. Okay, DNA storage, by the way, DNA storage, this is the other extreme. They're being considered for really extreme scientific data storage, meaning, okay, you generate humongous amount of data, you cannot afford to run data centers to store them because chances are you'll never use them in the next 10 years. Maybe sometimes in future, humanity will find a way to use all this data. So we are just gonna store it. Sometimes, this will sound crazy, I know. NASA engineers want to send out data about humanity in case something happens to Earth, like existential crisis. So they send out this data. There was a time where they used to send out CDs, but not anymore. They realized that they're not that good. Now they're planning to send out crystal memory and DNA memory. You see where I'm going with it? That the reason is their retention time is extremely high. I mean, I heard that some of these memories have retention time which is as close to the age of the universe. Okay, so like unreasonably low, but they will never lose data. That's essentially what I'm saying. Okay, so retention, there is a range. So when you're looking at a memory technology, there is a physical mechanism involved. That mechanism, spin transfer torque memory, spintronic memory, on the other hand, their retention time is extremely long. So we like them rather than going for DNA and crystal storage, which are very difficult to handle. Spin transfer torque memory is very easy to handle, by the way. That's why it's on the top of my list, by the way. Very good retention, magnetic RAM. Okay, moving on the next one. Endurance. What do I mean by endurance? How many times can you read and write this memory? Essentially write. Like, can you keep writing it over and over again? I don't know if you have ever encountered that. If you use a flash drive too many times, there is a chance that it will degrade and it will all of a sudden crash, depending on the underlying technology that was used to create that portable drive. Okay, so similarly, depending on whether you are using that memory in a dash cam where you have to continuously write and overwrite, that means there has to be continuous endurance cycle. Making sense? Or there are storage class memories where they can hold onto the data for a long time, but you cannot read and write them too many times, maybe a million times, which is good enough for some applications. Why am I telling you, this individually? Because like I said, there is no magic combination. We don't have a memory device that gives you the highest retention with higher endurance, with higher blah, 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 right? Nobody achieves everything. So you have to pick and choose depending on your application. If it is a data center, you definitely care about endurance because it is continuously communicating and changing the data and updating the data. So endurance matters. Retention may not be that much because you are not gonna save it for the long time and not use it. You are continuously using it. Okay. All right, without boring you too much, we will discuss. Oh, okay. Let me ask you a question before moving on to the next one. Why is there a retention time involved in some physical devices? Why cannot it be infinity for everybody? Why can't it be infinity? Yes. Thank you. Perfect. That's the perfect answer. Depending on which property you're using, that could lead to degradation and leakage. And at some point, again, it doesn't have to be completely erased. As long as it is degraded to the degree that we cannot sense it reliably. That's it, right? For example, I can talk about ferroelectrics. In ferroelectric material, there are domains, magnetic domains. And because of domain-domain interaction, gradually the domain relaxes to a preferred direction. So even if you write them into a different direction, they'll gradually always relax to the easy axis. I mean, depending on how long it takes for them to completely relax, you have that much time as retention. So that's one example. And there are many other physical reasons for other memories. So we have to be mindful that there is a physical reason behind these numbers. They don't just fall off the sky, right? Oh, take 1 billion as retention. No. Okay, so I'm not going to go through all of them, but we will cover all of them. You can take a look at this. If you have questions about any one of them, please let me know. Maybe I'll just cover one. MLC, multi-level cell. That falls under scalability. So every time we discuss a memory, like say phase change memory, I'll mention that this memory is particularly exciting because it gives you the opportunity to have MLC, multi-level cell. Hold on a second. What does that mean? That means this will be good for scalability. You can scale the memory into like from gigabytes to terabytes easily. What does that mean? So far, all I've discussed about memory involves two levels that we could use to represent 1 and 0. I know I'm getting ahead of myself, but I hope it will make sense if I try hard and if you try hard to understand this. So we just have to represent 0 and 1. And I told you, if I try to represent 1 billion bits, I will need 1 billion distinct devices. People thought about, hey, what if we create a device that has 4 different states? 4. Like maybe let's consider low and high resistance. We could represent 0 with low resistance, 1 with high resistance, say. And that's how you use a memory. But what if I have really low, slightly low, kind of low, and high? 4 different levels in a material, say, then I could represent 0, 0, 0, 1, 1, 0, 1, 1. You see where I'm going with it? If the same device could have 4 different stable states, you could have used those states to represent 2 bits at a time. That means almost half, like basically to store 1 billion bits, you'll need 500 million cells. Now, instead of 4 bits, now if you could have 8 levels, you see, this is basically logarithmic progression. You could reduce the number of memory devices required to store information. That's called multi-level. So multi-level cells are dream combinations. We have some of them, but they're not ubiquitous yet. People are trying to make them. Anyways, things will get clear as we they will not make sense at this stage. I want to show you the extent to which we will discuss. Now, let me take a second here and talk about the uniqueness. The reason why this course is unique is because the requirements and the metrics are unique for memory devices. I'm not going to talk about the general requirement for electrons, only for the memories. Okay, move to the next one. These are realistic data. And by the way, for this lecture, you don't have to memorize or remember even any of them. They are meant to show you or open up your horizon. That's all. Okay. So if you are wondering, hey, what do we do with it? Right? You don't do anything with them. Okay. These are realistic data taken from research articles. So basically, there is a group who tested all sorts of emerging chips that the industry folks were working with. Notice the name: Samsung, Hitachi, blah, 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 right? I'm not going to go through the list. And they tested the storage capability for all of them. See, for some memory, and depending on the type of memory and the company that's making it, some of these companies were only able to make 10 kilobit storage, and others were able to make 100 gigabit, right? So there is a huge spectrum depending on the technology that they're using. They're all emerging memory. Let me point out, Everspin uses spintronic memory. Making sense? So you see the activities that are going on here, and these are only up to 2015. If you see the numbers beyond this, this will be even crazier. And they will, where should we target going? We should target going in this direction, basically, up, higher up, so that you could store more information. Now, take a look at this one. Test chip capacity, like how much can you store with respect to memory cell size. What does cell size mean? What is the size of one memory cell that could store 1 bit of information? That's the cell size. Obviously, just imagine if the cell size is too low, too big, that's not an ideal candidate for portable wearable devices. It could be a candidate for data centers, but for small scale footprint, you cannot use them, right? So notice this one is possibly the worst case scenario. I'm using it as a training tool to train you up into analyzing this type of information. This is the worst scenario. Why? It has the largest size, which I hate for most applications, and the smallest capacity. So it's possibly the worst. Okay. This is the best. Why? It gives you the highest storage capability with the least amount of cell area. So anything that is small could be used for portable devices as well as data centers. Data centers don't mind, by the way, but cell phones and laptops mind. Okay. So let's see who is this. Oh, this is a resistive RAM, as you asked. This is the memristive memory. So that's why they're very promising, and we'll talk about that. Okay. And who is the other guy? This is STT-MRAM, the memory that I was talking so highly about. But don't worry, don't discard them so quickly, because that's not the only STT-MRAM. Maybe one company tried making STT-MRAM and it ended up with this subpar design. But there are other companies. Look at this one. This is also STT-MRAM. Can you read this? Look at the color. Red represents STT-MRAM, right? There is a red dot right here, which shows really tiny footprint, maybe not as high of a storage capability, but very good. Not as bad as this one. Do you see that? Are you all good so far? Okay. So, I mean, why can't we just keep using this? Resistive RAM and problem solved. I told you, there are many other aspects. They don't give you high retention. They don't give you lower variability, but STT-MRAMs do. So you also care about retention. Yes. Oh yeah, thank you for asking. I haven't explained that yet. I will explain it when I go over the layouts, okay? Basically, if represents feature size, which I haven't discussed. One more thing, I want to show you, it was right here as well, in case you bump into it later on and, oh wow, many slides. Sorry, give me 1 second, let me find it. It was probably, no, okay, no, it's probably not here. That's okay. I thought that it was in a different slide as well, but thankfully it wasn't there. So in case you get confused with the unit F square, we typically measure the area, layout area, instead of using specific dimensions like micrometer, centimeter, stuff like that. We use feature size because feature size could be easily plugged in. And basically, if I tell you the number of F, say some nanometer, you could just put it in and calculate the total. It helps us keep things simple. Like see 20, 40, 60, 80 looks nice. But if it were like 12.7 micrometer square, it will be a little bit difficult to read. So it's kind of like the norm in the industry that we use feature size. The other reason is feature size represents the minimum dimension that you can create in a technology. So if I tell you, this is my minimum feature size, this is my minimum feature size, okay? So if I tell you that the area of a memory cell is F square, you think this is the ultimate. You cannot have a smaller area than this. You know why? Because that's your smallest dimension, that's your smallest dimension. There you go. But if I tell you that the feature size, this is an area, 4F, 2F, then you could negotiate. Hey, could you just reduce it to like 3F, 1F? Can you try doing that? You can tell your engineers to do that. But if your engineer comes and shows you, this is my area, done. Okay, sorry, man. I know you cannot do anything about it anymore. Did you get it? No. Okay, that's the other reason why people love using this type of notation that shows you how far away are you from the minimum achievable area in this technology. Maybe in the next generation, you'll be able to reduce. Who determines how small a feature can be? Do you know that? Who determines that? The machines that you buy. Lithography tools, okay? 335 folks, did I ever talk about it? There is just one company in the world who controls that advanced tool, ASML. Yeah, just Google it. Just imagine all these advanced chips that are being made everywhere around the world relies on one company, and ASML makes the tool. And they tell you that this is the smallest dimension that our tool can create. Sure, we'll live with it. Everything is related to that tool. In 5 years down the line, if ASML makes a smaller dimension capable tool, sure, you change the F and there you go. Your area will reduce, obviously, but you don't have to update this. Let me go back here. You don't have to update this graph. You just have to change F. That's all. Am I making sense? Yes. So 4F square, yes, it's a nanometer, of course. It's a nanometer. So the smallest feature size depends on the, typically that is related to the transistor technology, right? We often use the term related to, let me show you here. I don't have any, maybe this one. Maybe think of a transistor and the gate dimension. This is the gate of a transistor, okay? The dimension of the gate is typically considered as the feature size, because this is possibly the smallest thing that you create in a transistor, okay? It could be 3 nanometer even now in today's technology. It could be 3 nanometer. In theory, in research lab, it is actually getting even smaller than that. But in consumer electronic market, we are already dealing with 3 nanometer.
So it's dealing with the transistor gate size.
Gate size, yes, sure. Okay, so we don't have much time, but it's okay. We're almost there. Look at this other chart. Let's look. The reason for me to show you this is to educate you as to how to read this type of data from data. I told you I went through research papers, data sheets, industry reports, and textbooks, obviously. But textbooks are so far behind, as you can imagine, right? This thing is accelerating. Okay, so notice chip capacity versus write speed. Notice STT-MRAM. Depending on different samples, you can have 100 nanosecond to maybe 5 nanosecond of write speed. Am I making any sense here? In addition to that, basically, look at PCM, phase change memory. The write speed of phase change memory is all over the place. Who determines that? Depending on the underlying material that you're using. Different companies have PCMs, but they have different underlying materials maybe, and that determines the overall speed and overall capacity. So basically, this type of graphs bring together all these performance metrics that you should care about. Endurance is one of them. Capacity, storage capacity is the other one. Obviously, write speed is another one. But how many information can you put in one slide, one plot? Not too many. Yes. Yes, that's a great question. So that's a great question. It's not mentioned here, but it was mentioned in the paper. The size of the sphere typically represents the endurance cycle for this paper. Okay, so the bigger the sphere is, the more endurance you can get, right? But it's not obvious here. So people try to find interesting ways to represent more data in one plot so that you get all sorts of information in one shot. But even then, it's impossible to bring everything together. So you have to explore multiple. Okay, so these are all slides that I also used in 335. I want to just quickly go over them. Wanted to show you that semiconductor chips, not just memory in general logic, they're critical in our infrastructure. Without semiconductor chips, even car makers have to stop production because there is so much electronics in our daily items, including your toaster oven, your washer dryers, your refrigerators, everything, right? So obviously, when we talk about memories, they're not just in advanced data centers and in your cell phones, they're essentially everywhere. If I'm sure I went over this, any computing system that you can think of will have a memory associated with it. The next lecture, then lecture 2, will make it even more prominent. I'm dying to show you one diagram that will show you how much the memory takes up in an actual so-called processor. So the processor itself will be like gobbled down by memory within itself, not even considering the external memories that you're using. Okay, we are getting there. Anyways, I'm not going to go through these are like some screenshots from some news articles that showed how critical the chips are, semiconductor chips are in our economics in general. And that is leading to humongous amount of investment, billions of dollars. These are old data. There are many new investment. Micron Technology, who is the biggest memory maker in the US, they recently got some federal grant to create a new fab in New York. They were previously only based in Idaho, but now they're getting to New York as well. So they're expanding. This is the last slide for this lecture. And I think I kind of went over it in the last lecture as well, very quickly. Just one example. Something that you probably wouldn't have thought about on your own. Scientific experiments like what CERN scientists do in Large Hadron Collider creates a humongous amount of data, so much so that they could be the sole customer of Micron, for example, if they want to. Like, they need so much storage solution that simply buying off-the-shelf storage will not work. And just working with a cloud provider will not even work. They work with Micron to build on-site data center specifically catered towards their needs. So just imagine, these are stacks of data storing machines that they use on site. Okay, and just look at the amount of data that they're generating, starting from petabyte to thousands of petabyte. And if you want to put them in context, this is how the numbers look like. I'm sure we are all aware of gigabytes. So giga to tera, tera to peta. In fact, very recently, they have exceeded exabyte. So like insane. I mean, if you could just survive as a company with these guys as a customer. That's what I wanted to tell you. Okay, so this was supposed to be the last slide of first lecture, and it is over now. I still want to just open up lecture 2. I know we don't have much time, and just finish one slide because I think that will put things into really nice context for the next lecture. Okay, this is how the memory hierarchy looks like for a typical server, and I'm going to show you the same hierarchy for a mobile device. Why? One is a large scale system. You don't care about area. The other one is a small scale system. You care about portability and energy efficiency more often than so. So this is CPU. This is your processing unit, logic, like all that you have learned so far, 433, 255, digital logic design, whatever. They taught you CPUs, basically, whatever you need to make CPUs, logic and whatnot. Now take a look at, in that system, this is a server. And this is taken from a computer architecture textbook, not for a memory textbook that they're trying to oversell memory. No, this is a computer architecture textbook, okay? You can look it up. Registers are essentially memories. They store information, but very small amount of information. Beside that, you need cache memory. We'll discuss all of this in the next class. This is level 1 cache. And then you need level 2 cache. That's again memory. Then you need level 3 cache, again memory. Cache memories are fast, like really, really fast. And then you need actual memory. This is memory, but these are storage class memory. And then finally, you need disk storage, something that you just set aside. So this is taken from a computer architecture textbook that showed the extent of memory that is involved in simply making a server. And CPU is just one of them, okay? I want to quickly point out that for mobile devices, the only difference would be you need less cache. You have less number of cache levels because you want to save area and you want to save energy, because cache take up more energy. Notice one more thing. The closer the memories are to the CPU, look at the speed, 300 picosecond, 1 nanosecond, 10 nanosecond, 20 nanosecond, 100 nanosecond to millisecond. So the farther out they go from the CPU, the slower they become. That's by design. That's how the architecture works. If you need quick support, just take it from the cache nearby. But the cache cannot handle everything. Otherwise, it will literally, I'm not making it up, it will literally burn the CPU. It will generate that much heat. Anything that, when something works, it generates heat, okay? It will create that much heat that it will burn down the CPU. So we distribute it. Like just use some cache, quickly work with the CPU, and whatever you need, the next level cache will actually feed the next set of information to this cache. And meanwhile, the other cache will feed information to this cache, okay? It's like working in a team where your friends are bringing some stuff one by one and you are just doing the work. All right, so we'll get back to this in the next class. Just wanted to, bring it in front and show you how critical memories are. Thank you.